So in Algebra 1, you talked about the properties of exponents, and now we're going to use those exact same properties to look specifically at expressions where the exponents are fractions, where they're rational numbers. For example, in the box on the top left-hand corner, we have the product of powers rule. So this tells us that when we have two terms with the same base, we can add their exponents. So x to the power of 5 times x to the power of 3 is x to the power of 5 plus 3. Or x to the power of 8. And it works the same way with fractions. This is going to simplify to 8 to the power of 1/2 plus 2/3. And now we just need to remember how to add 1/2 and 2/3. Once we've got a common denominator, we can see that that's going to be 8 to the power of 7/6. And that's our final answer there. So we used the same rule. We are just adding fractions instead of adding whole numbers. Let's try it now with our quotient of powers. So the top right box. Here on the top one, we have x to the power of 5 divided by x to the power of 3. And we would just subtract 5 minus 3 to get x to the power of 2. Well, we're going to do the same thing with our fractions. Remember I wrote these with a denominator of 6 earlier so that I could subtract them? Well, now it's easy. I can see that I'm going to have 8 to the power of 3/6 minus 4/6. Which is going to give me 8 to the power of negative 1/6. Now, of course, I could simplify that further, but for now, I'm just illustrating this one rule. So I'm just going to leave it right there. Now, sometimes we have what we call a power of a power, which is where, for example, x to the power of 5 is raised to the power of 3. In that case, we just multiply 5 times 3, and we have x to the power of 15. And that works the same way with our fractions. Remember, when you multiply your fractions, you just multiply the numerator times the numerator and the denominator times the denominator. So you would have, in this case, x to the power of 2/6, which reduces to x to the power of 1/3. Now let's look at radical expressions over here. We know that we can write x to the power of 5/3 as x to the power of 5 cube root 3. Similarly here, for 8 to the power of 4/2, we could write that as 8 to the power of 4 square root. Just for fun, I am going to simplify this one. So that would be 8 squared, which is 64. Just as before, we know that any number raised to the power of 0 is 1. And then again, if you have a negative exponent, you move the base to the denominator and make the exponent positive. So x to the power of negative 5 would be 1 over x to the 5. And x to the power of negative 1/4 would be 1 over 8 to the 1/4. And of course we could simplify that further, but for now I'm going to leave it here because we're focusing on this one rule. If you'll look with me at your assignment today, you'll see that these examples combine multiple rules at once. And I want to look at number 2 with you. So for number 2, I noticed that I can't really do 36 divided by 16 and end up with a nice, pretty even number, but I do realize that both 36 and 16 are perfect squares. I could actually rewrite this as 6 squared over 4 squared, couldn't I? And when I write it that way, it's really easy to see that the square root is going to be 6 over 4, or 3/2. And now we're done. How about this next one? Well, there's a lot of right ways to approach it, but the first thing I notice is that these have the same bases. So I can subtract. I can write 3x to the power of 4 minus 2. So that's 3x squared. That's 3 squared times x squared, or 9x squared. And now we're done. We can't simplify anymore. This next one looks harder, but it's really not. Using the power of the power rule, this exponent applies to all 3 pieces within inside my parentheses. So I'm going to rewrite 8 to the power of 1/3 as the cube root of 8. I noticed that my x to the power of 3, when raised to a power of 1/3, I'm just going to multiply those fractions, and that's going to be x to the power of 1. So just x. And then 27 to the power of 1/3 is the same thing as the cube root of 27. Well, I know 2 times 2 times 2 is 8, so that's a 2. And 3 times 3 times 3 is 27, so that's a 3. So I have 2/3 x as my final answer on this one. So in this case, I'm going to apply my power of 1/3 again to both the numerator and the denominator of this fraction, so that I have 2 times the cube root of 1 over the cube root of 8. Well, the cube root of 1 is just 1, and the cube root of 8 is 2. So this is 2 times 1/2. And 1/2 of 2 is 1. How about one more example? You want to give it a try? Why don't you pause the video and see if you can do this one? Here's a hint. My first step is to write down the numbers inside of my radical as factors where I am showing the factors that are perfect cubes. So for example, 27 is a perfect cube and m to the power of 3 is a perfect cube. What that allows me to do is take the cube root of 27 outside. That would be 3. The cube root of 27 is 3. And the cubed root of m to the power of 3 is just m. So that m can come outside too. So I took these outside. What's left inside? Just my leftover 2 and m. And then outside of my radical, now I have 2 times 3 times m. That's 6m on the outside and 2m on the inside. And I don't want to forget my index of 3 there. All right, so that's my final answer there.